Everyone, so today we're going to go ahead and code up our Triton kernel. When you're doing kernels, you actually end up having to code two components, so the kernel itself, but you're parallelizing that kernel. In other words, it's going to be run many instances at the same time, hence the parallel programming aspect. So as a result, you need to have a driver program, and the driver program will go ahead and set up a lot of the meta information in terms of how many, the block size, and how we're going to parallelize said kernel. So let's go ahead and get going, and hope things will be clear as we code this out. So for making a kernel, you do have to use this decorator, triton.jit, that will force it into the compiler, the Triton compiler specifically. So that is your decorator to tell that this is a Triton kernel. And let's call this underscore softmax forward kernel. Let's code up the driver program first, because we're kind of take a top-down approach here in terms of laying things out. So we'll just put a placeholder for now for the kernel itself. And then here's our actual Softmax implementation. Just like the naive version, it's going to take a single tensor input, return a torch.tensor output, quick doc string, Triton impl of Softmax, forward pass only. I do have the full Softmax forward backward and also multi-dimensional tensor handling in the repo if you want to take a look at that, and maybe I'll make a video on that later, but for now we're focusing on effectively an inference kernel here, just a forward pass. So let's see, once it comes in, we have to start doing the pointer arithmetic. So this is kind of where you start seeing that in exchange for having that fine-grained memory access, which lets you produce more performant code, we do have to handle a lot of overhead in terms of the memory access. So let's start with that. So we're going to have to understand the shape of the tensor that just came in. Let's just make a quick assert for safety. X.dim. I'm basically just checking to make sure right now we only handle 2D tensors. We don't handle things like batches and so forth. And the full kernel that I have in the repo, we do handle that, but we'll do that later. So accepts 2D tensors for now. Okay, it's a quick safety check there. Now we need to start getting into some meta related information. So how are we going to set up the kernel? So for this particular kernel, we're going to parallelize along the rows. So basically each row will become its own kernel instance that will get passed in into our kernel up here. So if we had 1,000 rows, we'd end up launching effectively 1,000 kernels to be parallelized at the same time, each processing a row. So we need to set all this up. Block size would be our first piece of meta information. And to do that, we're going to take the columns. So block size is related to the chunk. So we're parallelizing along the rows, but we need to then chunk out how we're going to handle, in this case, the row itself. So we're going to do that by taking the column shape. And we're going to use this other function called next power 2, and passing calls. So what happens here is if, for example, we had 1,000 columns, 1,000 columns in the input, this would actually become the block size would effectively end up being 1024. And so as you'll see, the second chunk would end up having, or at least one of the chunks, the last chunk, would end up having additional space that it has to handle. And so when we do the masking in the kernel, that's to protect, to ensure that we're actually only accessing valid data and not the entirety of what we've actually allocated here in the block size. So the other thing, setting the num warps, and this is kind of like a thread density, I guess this is the short explanation of it, equals 4. If we have larger amounts, we want to increase the number of threads. So this is really 4 times 32 threads. So each warp is 32 threads. And so if block size, so let's pick 2 powers of 2 here, 2047, so basically short for 2048 with just a single check. Then we'll change num warps to double, and if block size, greater than 4095, just saving a single comparison here, this is really 4096, num warps equals 16. Okay, so that gives us some of the key components for the meta information. The other thing is we need to explain how we're going to parallelize it. So I like to just lay out the grid directly. It needs to be an iterable, so we'll take the tuple of the rows, because as I said, we're going to parallelize along each row in terms of a kernel instance there. So grid equals rows. I think what else we need here. Gives us our meta information. We need to allocate our output buffer. Let's scroll up here. And we can just mimic the incoming X. And so let's call this Softmax out equals torch.empty like, oops, like X. So this will give us a duplicate copy, but a blank slate, so to speak. So same device, same dtype, etc. as our input. So that's what we'll be writing back out to. And with that, we can actually launch the kernel or call the kernel itself. So softmax forward kernel, we need to pass in our grid here as the first parameter. Now we get to the actual functional parameters, which we haven't written yet. So let's lay these out. So what I like to do is output buffer first. So that's going to be SM, let's do this, SM out. We need the stride. So everything in memory is not a logical representation, so a 2x2, for example, tensor is really laid out as a 1D. And so your stride to move between rows is basically the width of one column would get you to the next row. So we need to pass in the stride for a given row. Let's kind of see, there we go. So this is going to be smount.stride row. So that, well, that's annoying. Smount stride. And then we have our input buffer, so that's just X. And then we have X dot stride. What? I don't know why it wants to keep adding that. Anyway, X dot stride. So input buffer, output and input. We are going to mask along the number of calls. And lastly, we need to pass in our metadata. So block size, and num warps. This will actually be absorbed by the compiler. It won't actually flow into the kernel itself, but warps. And once we're done with that, we would just return this out, which is our buffer that we'll write back to. So I think that looks good. So with that, we're parallelizing along the row dimension here for the grid. We've got our output buffer, our inputs, our strides, the columns to do the masking, and the block size that we're chunking along. And that should cover it. So let's move into, and we're turning the output. So let's go ahead and move up to our kernel itself. So we need to accept the incoming stuff that we just passed in here. So this is going to be output pointer. Let's go stride, output row, input pointer, another stride, input row dimension, calls for our masking, and block size, which we flag as a const expression. Yep, that should do it. So once we jump into the program, so remember we're going to have a lot of different programs all along the row being launched and coming, so we need to figure out what row index are we, and that's going to be based on program ID, which is the kernel ID effectively, and 0 dimension, so the row dimension. So let's put a comment here. The first thing we have to do is basically set up our input pointers before we start doing anything. And this all starts with understanding our row index. We're then going to move into, from the input pointer, we need to get our access to the row pointer, row start pointer. That's going to equal input pointer. So we start at our base, and now we're going to add the stride times the row index. So in other words, if we're row 3, we need to jump effectively 3 rows, which is 3 strides in to get to the proper row. So that's going to be row index times stride input row. Okay, so now we're starting to look at the row, but we need to understand how many columns do we have here. And so that's going to be based on the block size, which is what we're chunking along. And so block size, we need to set up our call offsets. Offsets calls. Let's just call it call offsets. And that's going to be, we need to get a range here. This also kind of enforces that, yeah, this must be power of 2 thing. So we're going to start at 0 and we're going to go up to block size. So that tells us how many particular chunks of the row here to process. Although right now it's really just going to be a single row at a time. So call offsets equals t.range. And from there we can actually get our actual row itself by setting row.pointer plus call offsets. Okay, so that should give us full access to the entire row. So actually, we've laid out where we're starting with our pointer. We actually need to load the row. So let's not call this row. Let's call this input pointers. And from there, now we do the most important part, which is now that we have the pointers pointing to the right place, we can go ahead and pick up the row from HBM and move it to SRAM. So move to, and that is done with tl.load, and our input pointer, oops, so this will be the row. We'll pass this back once it's loaded. Input pointers, and mask, as I talked about. So mask, we want to use call offsets, and let's set up a generic mask because we'll reuse it when we write back out. So let's just call this row mask equals call offsets must be less than num call. So this is why we passed in the num call so that we know what's the valid data versus not, because this is being done on a power of 2 basis. So we're basically almost always going to have, not almost, well, in many cases, we're going to have excess. So we need to mask this out. And so we'll pass this mask equals row mask. That will make sure we don't inadvertently access anything beyond the actual data. There's this other flag called other, and that's just going to fill in what's left over with what can be considered as a signal that it's invalid data. And we can just do negative inf. So that should cover it. So at this point, we've got our mask, we loaded it. Now we actually have our row. Now we can actually start Softmax itself. So you can see we have a lot of memory overhead involved, but that's the trade-off of being able to get faster memory total performance by having finer grain control. So we have our row loaded up. So now we need to move into the actual Softmax itself. So first thing we need to do is get the row max, tl.max of the row axis, I think it's axis, is row dimension. And now we can say row, safe row equals row max. And we can get rid of this intermediate. We're basically just doing a 2-step thing. We can just make it a 1-step thing there. So basically, as you recall from the naive Softmax, first thing we do is unscale, I'm not sure, descale, anyway, reduce the scale by removing the max from all entries. So now we need to exponentiate. So let's call this numerator. So tl.x. And to continue the exponentiation here, so we need to just pass in safe row. That gives us our numerator, denominator. It's going to equal, we need to sum up the numerator. And we need to do it on the row axes, right there. And finally, our SM out here is numerator divided by denominator. That's it. So we've completed the Softmax itself. And now we need to do the pointer arithmetic to set things up so we can write back to the output buffer, basically moving things from SRAM, which is where we're at currently, and move it back out to HBM, or global memory. So let's see, write back to HBM. So we need to set up our output pointer now. So our output pointer index, output row pointer is going to equal start with output pointer and add row index, which particular row we're working on, times output pointer stride row, or stride output row. Now we're pointing at the right row, and of course we need to load up the columns. So output pointers is equal to output row pointer plus column offsets, so that flushes out the row column dimension here of the row, and at that point we just do a TL store, and our pointer is this guy, output pointers. What are we writing? Softmax output, and our mask is the same as before, the row mask, so they're only writing relevant data. And that should be it. So let's just take a quick review. Passing everything in, our row index to set up our input pointers, get to our input pointers, our row mask, load the row, run the softmax itself, and write from quote-unquote on-chip or SRAM, and bring that back up to global memory with the tl.store, and we're returning here on the helper function. So I think that does it. So let's take a look at what we've done, make sure everything works. So this would be Triton out equals softmax sample, and print those results. Remember, this is a very small sample, so we can visualize what's happening, or visualize the results. Triton out equals, and we can go ahead and run this. This is blank up high. Where are we? Demos. Okay, so that's running. No errors yet. Oh, first time, no errors. All right, great. So as you can see, we've got our reference out, which is our PyTorch Softmax 017 317 861 234 16364, and we just focus on the last one, 6364. Oh wait, hang on a second. Something's off. 6364 2341. Right now. This is odd. We have an inversion here. Something's off with our stride. All right. So actually, I found a mistake here. So it's actually probably a great example of what can potentially go wrong with your memory access. So it's actually not actually the stride. What's happening is we were rewriting the same row output over and over, because look what's happening. We're going to write back out to HBM. So this is our base pointer, and then we're doing the row offset, at which point we need to then expand out column-wise. The mistake that I made here is I reused the output pointer, so basically resetting, so we'd be effectively writing the same row over and over, and that's why we had the, if you look down here, it's literally duplicated row. So this needs to be leveraged. Once we have our row pointer, we need to build on that specific row and then add the column offset to get our output pointers. I actually think I want to functionalize this type of pointer arithmetic, so this is probably a great example of a motivation to actually do that, to avoid these mistakes by just passing in what you need to get and have the kind of an efficient function to do the pointer math for you and reuse that. But anyway, so with that fix, I believe we will be back in business here. So let's run this. Much better. Okay, and this is kind of one of the reasons that I had in the sample sort of an up and down effect here. Where's our sample? Yeah, 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. So very easy to visually check what's going on. So let's double check things again. Our reference architecture is 017 to 6364. We have same, and then in reverse, descending order, and reference, descending order. Great. All right, so there we go. So we've got a working forward Softmax kernel in Triton. So the tutorial that I'm basing a lot of this off of, it has a nice benchmark setup. So let's put our kernel to the test here and compare it with a whole series or range of tensor sizes, and we can see the performance gains here. So naive softmax, I think we're ready to push this over. This is our demo softmax, so we need to move over our Triton kernel and our helper function like this. Let's move this here. Yeah, we've got our naive softmax here already set up. Okay, so that's in. Here's the benchmark code. So I'm gonna make sure what it's calling, softmax, okay. And so here we have torch, ours, and naive. And if you run this yourself, one thing to note is you do need to pass in the path, otherwise you won't actually save out the images. I'm not in a Jupyter Notebook, so it won't just automatically pop up. So I think with that, we're ready to run, and let's see how we do here. So Python demo, and this takes about 30 seconds. So I'm running this on an A10 for reference. I also ran on A100, so I'm kind of curious to see how the two compare. Like I said, this takes about 30 seconds. So while we're waiting, as I mentioned, I do have the full Softmax version in the repo, and that gives you the forward and backward pass. And I actually used that for some end-to-end training yesterday, so that was actually pretty cool to put that to work. So let's give this a few more seconds and see when the results pop out here. Probably could use a progress meter. There we go. Okay, so let's take a look. So what do we have here? So n is the tensor size, or sequence length in this case, number of columns. And so comparing at the start, we get Triton. So by the way, this is gigabytes per second output measurement. So 372, Torch native is 409. So Torch is just slightly faster for the smallest tensor. And our naive implementation, of course, is significantly slower, almost 3 times slower. And as we jump up here to 768, now we're starting to beat out Torch here. And we do this whole roll through all of the different tensor sizes. And when we get to these giant tensors, we can see we're handily beating PyTorch. So it looks like they've kind of optimized for the more common use case, which would be arguably smaller tensors. But let's take a look at the visuals on this. So we can make this bigger. There we go. Okay, so nice. So what do we see here? We see that Triton is the blue, green is PyTorch native softmax function, and the one that we wrote, the eager, so-called torch JIT, but that's our eager mode that we wrote, or just straight PyTorch code. It's relatively speaking quite slow, so it's not really even in the running. And here we see kind of in this range up to 2000. Well, interesting tip there. I think it looks like they've kind of tuned for 2 different scenarios. But anyway, as the tensors get larger here, we can see that Triton continues to perform admirably, and we see a steady decline in PyTorch performance. So this is on A10, it's a little bit different on the A100, but hopefully it gives you a good idea of some of the performance potential you can gain by writing your own Triton kernels. So hope this was informative, and I'll see you in the next video.